Hello, my name is Joachim Meyer and I'm a PhD student at Saarland University. During my time at Heidelberg University, I investigated compiler optimizations for the ND-range parallel 4 paradigm in hipSYCL. The main goal of our work is improving the performance portability of ND-range parallel 4. This is generally interesting as most heterogeneous models provide similar hierarchical execution models. The hierarchy is tailored to the GPU's architecture though. This renders efficiently mapping the paradigm onto CPUs non-trivial. For library-only implementations of SYCL, the requirements of workgroup synchronization degrade the performance heavily. This is where we try to help. Before we get into the topic, let's give a short introduction to hipSYCL. hipSYCL is a multi-target SYCL implementation that's mostly driven by Uni Heidelberg's Axel Alpay. It reuses already existing Clang toolchain, augmented with a Clang plugin to target GPUs. It also features an OpenMP CPU backend that can be used in a library-only fashion. This means wherever you can compile hipSYCL, you can use SYCL on CPUs. One major issue of the hipSYCL CPU backend is the performance of the ND-range parallel 4 paradigm. In this example, we see a SYCL reduction kernel that uses global size number of work items, which are then divided into workgroups of size group size. The reduction is performed on a local memory array. The local memory array is called Scratch. The accesses to the local memory are ordered by the barrier. The barrier synchronizes all work items in a workgroup. Therefore, the semantics are: if one work item reaches the barrier, all work items have to reach it before execution of the kernel can continue. On GPUs, this can be implemented very efficiently. This is due to having many more or less independent threads that execute the work items and therefore provide the necessary forward progress guarantees. In hipSYCL, we can just use the sync threads primitive. On CPUs, on the other hand, we first have to find a good mapping of ND-range's hierarchy to the CPU. The original approach from hipSYCL prior to version 0.9 is to use one thread for each work item. By using OpenMP parallel 4, we can then just use OpenMP barrier to implement the synchronization. This requires potentially many operating system threads though. The context switches and scheduling overhead make it very inefficient. Additionally, it is not possible to vectorize across work items. In the 0.9 update of hipSYCL, this approach has been replaced by an implementation using Boost Fiber. Boost Fiber provides lightweight threading and synchronization. With this, it is also possible to greatly optimize ND-range kernels without barriers. To do so, the fibers are only spun up if the barrier is encountered. Otherwise, the work items are just iterated over. The barrier case still suffers from many context switches and also scheduling overhead, as well as limited vectorization across the work items. Our work investigates two approaches to improve the performance of the parallel 4 paradigm. Both approaches improve the performance by parallelizing over the workgroups and executing the work items in the single thread of a workgroup. This requires a compiler extension to split the work item loop at the barriers, so that the semantics of the kernel are preserved. Our implementation of these approaches still supports all CPU targets that Clang supports OpenMP on. This is without requiring the availability of an OpenCL runtime, which most other SYCL implementations do. The first of the two approaches is taken from the portable OpenCL runtime known as SYCLcon. Here we see the simplified visualization of a simple kernel. The kernel has a basic block containing a barrier. The basic block is surrounded by a work item loop iterating over the workgroup. On the right side we see that the part before the barrier A1 and the part after the barrier A2 are now both surrounded by their own work item loops. The second work item loop is executed as soon as the first work item loop finished executing the first part of the kernel for all work items of a workgroup. The alternative approach we compare SYCL against is continuation-based synchronization. This was first presented by Karenberg and Hack. CBS first gives every barrier an ID, where entry and exit of the kernel have special IDs 0 and -1. Then, starting from each barrier, a depth-first search is performed, identifying barrier-free subchief keys. Here, we first find A1, and then from the barrier we find A2 as independent subchief keys. These subchief keys are then replicated and embedded in their own work item loop. The subchief keys are identified by the entry barrier's ID. Upon exiting the subchief key, it is remembered which barrier was reached. This is used to select the subchief key that shall be executed next. With this, the original kernel CFG is preserved. While adopting and evaluating both approaches, it became apparent that SYCL's approach had a semantical mismatch with SYCL's barrier model. SYCL only requires that a barrier must be reached by all work items of a workgroup if it is reached by any work item therein. POCL additionally uses a restriction from an early OpenCLC standard, where the number of iterations of a loop that contains a barrier had to be uniform for all work items. For this kernel, this is not the case, as a local ID is used in the upper bound of the loop. As a barrier is only reached on uniform iterations, this kernel is valid according to the SYCL specification. POCL uses the first work item to decide whether the loop shall continue iterating. This leads to wrong results for all but the first work item. For the performance evaluation of our approaches, we use two ARM as well as two x86 systems. The first benchmark is a SYCL bench reduction. The graph shows the speedup over the current fiber implementation. The hierarchical data point uses the hierarchical parallel for workgroup paradigm to write the reduction kernel and serves as a practical performance target. CBS-MUN is the only data point where the work item loops were generated inside the compiler. For the other two, the loop was written in C++ and then split by the compiler. For the latter, loop nests are collapsed for simplicity of the transformations. Overall, we can see that the loop vision approaches achieve great speedups of multiple orders of magnitude over the fiber implementation. Except on the A64FX, the loop vision reaches the same order of magnitude as a hierarchical one. On A64FX, LLVM's immature SVE vectorizer seems to be the main caveat. The various loop vision approaches do not differ too greatly for this benchmark. Another application we looked at is a dgem kernel. We additionally ported this to the OpenCL and show the results using the POCL OpenCL runtime as a reference. We can see that the hierarchical parallelism outperforms all other variants, as it apparently exactly matched an optimization pattern in LLVM. Apart from that, it is notable that on x86 hipSYCL outperforms or at least matches the OpenCL implementation. On ARM it is vice versa though. Note that the CL REPL variant represents fully unrolling the work item loop. This is only possible when knowing the workgroup size at compile time, which hipSYCL currently does not. As dgem is a two-dimensional kernel, we can observe that not collapsing the work item loop nest, but instead generating it inside the compiler does indeed help the CBS-MUN variant's performance. This is due to simpler index calculations that are better supported by LLVM's vectorizer. I want to conclude by directly comparing the POCL and CBS variants. The main issue with POCL is that it does not support the full flexibility of the SYCL specification, whereas CBS does. POCL's vision approach leads to linearized control flow, which can be beneficial for vectorization but also increases the code size slightly. POCL also requires some additional compiler flags and has more special case handling for control flow structures. The current implementation of both POCL and CBS show a geomean speedup of 23 and 34 respectively. Here it has to be noted that the CBS variant has been better optimized in hipSYCL. Summarizing, we can present the following impact of our work on the SYCL ecosystem. By improving hipSYCL's CPU backend performance using loop vision significantly, we are able to run SYCL code efficiently on any CPU that Clang targets. We are able to do so without any additional dependencies like an OpenCL runtime. We chose to upstream the CBS variant to hipSYCL. This is available from version 0.9.2, so go and test it now. Lastly, I would like to spike the discussion whether or not it would be a good idea to have something like the CBS transformation passes upstreamed in LLVM. This could benefit CPU runtimes for various heterogeneous models like OpenCL, CUDA, HIP and more. Thank you so much for tuning in. I look forward to discussing your questions and feedback.